Hi, I'm Trent Parado, Public Affairs Officer at NASA headquarters in Washington. I'd like to welcome you to today's news conference to discuss the first results of the Alpha Magnetic Spectrometer experiment. AMS is a state-of-the-art cosmic ray particle physics detector located on the exterior of the International Space Station. For those joining us online, you can find out more information about AMS and the International Space Station at www.nasa.gov/station. As for the order of events today, we have 4 speakers joining us. Each will provide brief remarks, and then we'll open the floor and phone lines for questions and answers. I'd like to take a brief moment to just welcome and introduce the speakers. Here in Washington, we have William Gerstenmaier, NASA Associate Administrator for Human Exploration and Operations. Here also we have Michael Solomon, Program Manager for AMS at the U.S. Department of Energy's Office of Science, and Mark Sestilli, NASA's AMS Program Manager. Now, joining us by video link from the European Organization for Nuclear Research, or CERN, in Geneva, Switzerland, is AMS Principal Investigator and Nobel Laureate Samuel Ting of the Massachusetts Institute of Technology. And with that, we'll have opening remarks, and I'll hand the discussion over to Mr. Gerstenmaier. Bill?
Thank you, Trent. It's my honor and privilege to be here today. Some days that my job is really great, and this is one of those days when my job is really great. And the reason it's great is I get to recognize a team that has put many, many years of hard work into an activity, and they finally get to see the fruits of all that labor, all those hours of putting this instrument together, to actually see it come together to get good results, and not just first light, but to actually have the first paper published and to have that discussion occur today in CERN with Professor Ting. So I'm so happy to be here with this group, and I know how much dedication, how much work they've put into this effort, and to see this wonderful instrument yield the results that Professor Ting talked about earlier today is just outstanding. I look at this as maybe the first of many of these events. I think the data that he shows today and the data he talked about today is intriguing and is very interesting. There'll be more discussions on it from those that can describe it better than I can. But I think it's just kind of the beginning of other great things that will come from this instrument on board Space Station. Space Station is a really nice platform, well suited for this instrument. It allows for a long, long duration of observation time, which is important to this instrument. We can essentially use decades of observation time, which will help reduce the statistics in certain low frequency events, and Station is a great platform for that. So the Station is a good platform. This is a good indication of some of the results that are going to come from Space Station in the future. So I'm, again, very excited to be here. So again, I'd like to thank Sam and his team for all the work they've done for this truly international team that has brought these first results to us today. I'd also like to take a special chance to thank DOE for their involvement and their support of this activity. Without them, this instrument would not be on orbit today. So they hung through a lot of tough times with us. They worked through a lot of integration issues with us, and DOE was a tremendous supporter of this activity all the way to where we are today. So congratulations to them as well as the AMS team. So with that, I'll conclude my remarks and turn it over to the next speaker.
Great. Thank you very much. I understand we're having just a bit of technical difficulty in our connection to Geneva law, so as we try to reset that, let's go ahead and start with Michael Solomon for a bit of information on some of the results that came out today.
Before we hear from Professor Ting, I'd just like to put the issue of these exciting AMS results, which you'll hear about shortly, into a larger context in our global search for dark matter. As you know, the question, what is dark matter, is considered to be one of the most important questions in physics. Our standard model of particle physics, highly successful, predicted the Higgs boson, which was recently discovered, has no place for dark matter. What that means is if we detect dark matter and learn something about its nature, we will have made a major impact to our understanding of physics and nature itself. So what is dark matter and how do we detect it? We know that we live in a sea of dark matter. Our galaxy is embedded in a huge, roughly spherical halo of dark matter particles. We know that dark matter interacts gravitationally. That's how it was first detected. But we also know, apparently, that it doesn't interact with light, hence the term dark matter, and it doesn't experience the strong or nuclear interaction. So how does it interact with nature? A class of models predicts that dark matter will interact with atomic matter in a manner very similar to the way neutrinos do, which means every once in a while there will be a rare interaction with an atomic nucleus that we can detect. How do we find dark matter? Well, there are three complementary methods of detection. And I want to mention the Department of Energy supports efforts in all three of these methods of detection. One is to look in accelerators. Accelerator collisions at high energies produce a wide variety of particles. Perhaps dark matter particles or their relatives are produced in such collisions. Searches have been made for these. They've not been found. So accelerator experiments have not yet yielded any evidence for dark matter. Direct searches for dark matter. We live in a sea of dark matter particles. Deep underground, all over the world, are many experiments searching for those interactions, those rare interactions of dark matter particles with detectors. If there are some interactions that are seen, and there are several, we can actually learn about the characteristics of dark matter. To date, underground direct searches for dark matter have yielded no conclusive results. That leaves us with the third and final method for dark matter detection, and that is through the indirect observation of the products of dark matters when they annihilate in interstellar space. A class of models makes this prediction that occasionally dark matter particles will annihilate each other and produce high-energy photons, gamma rays, and high-energy electrons and positrons. There have been searches for all of these. Searches for gamma rays from the galactic center resulting from dark matter annihilations have been done with ground-based instruments and space-based instruments, such as the Fermi Gamma Ray Space Telescope, which is also a DOE-NASA collaboration, and nothing has been found. That leaves us with positrons, cosmic ray positrons. There have been a number of experiments done, balloon experiments and space experiments, that have looked at the spectrum of cosmic ray positrons. If there exists a new source of positrons, such as through the annihilation of dark matter, we would expect to see it in the fraction of cosmic ray positrons that we see. And in fact, such an increase has been observed. First a couple decades ago by balloons, more recently with the Italian space satellite Pamela, and then more recently with the Fermi Gamma Ray Space Telescope. AMS has made a major impact on this final method of detection, cosmic ray positrons. These other experiments have in fact observed this type of increase that one would expect from dark matter annihilation. What AMS has done is made a high precision measurement of the spectrum, and it's detected spectral features which perhaps in the future can provide us with additional information on the nature of this excess. Now, I have to say, it's very important to say, there may be a very common prosaic explanation for this excess. It could be due to pulsars, for example. We don't know. The fact is, AMS has made a high precision measurement, and in the future, with more statistics, we're going to learn more about the nature of this excess. And if nature is kind, we might have a very exciting discovery in the future.
Great. Okay, thank you very much.
By the way, excuse me, I'm sorry. I would like to take this opportunity to congratulate the AMS International Collaboration on producing a flawlessly performing experiment. And I would also like to thank NASA for its superb performance in getting the AMS onto the International Space Station and helping with the continued operations. Thank you.
Great. Thank you, Mike. We'll continue here in Washington with our next speaker, Mark Sestilli. Mark?
Could I have the next image, please? Yeah. Okay, I chose this image because this was taken roughly about 2 years ago when AMS was first being installed. At that time, it's fair to say that AMS started a science voyage of exploration into our galaxy and beyond. Like all voyages of exploration, we had our share of Columbuses. And I think it's only fair to acknowledge some of those, both past and in the present. Going back some 19 years, okay, DOE people like Wilmot Hess, John O'Fallon had the scientific insight to select AMS as a concept from Professor Ting. In that same time frame, roughly speaking, former NASA Administrator Dan Golden had the vision to see that AMS was perfect for the space station. At this time and in the past, there are many very fine engineers at the NASA Johnson Space Center. Trent Martin, Ken Bolwig, Chris Tutt, Tim Urban, Phil Mott, many others, okay, whose tireless dedication over many, many years made AMS possible, and was made possible the ability to take an experiment that prior was done in vast underground facilities, okay, and then be packaged and be able to be put on the space station, okay. At the Kennedy Space Center, okay, again, many fine engineers that worked for many, many months to take the AMS and its very unique set of handling requirements and prepare for the space shuttle ride. At the Marshall Space Flight Center right now, as we speak, a team of dedicated engineers are working to keep AMS operational and coordinate the AMS with the control center at CERN. And we can all take pride in what they are doing. And as Michael said a moment ago, we're looking essentially at a glimpse of the future here. And make no mistake about it, there will be other glimpses from AMS in the future to come. This is a long-term program suited for a long-term vehicle, the space station. This is what station was built for, and essentially AMS is going to essentially carry through this. I have no more.
Great, thank you very much. And I'm pleased to say we have a connection with CERN in Geneva, so let's go there for remarks by Dr. Ting. Sir.
Good afternoon. AMS took 16 years to build. What it made possible is through the strong support of NASA, particularly Dan Golding, Bill Gerstenmaier, George Abbey, and many, many others. Also from the Department of Energy, Office of High Energy Physics, Jim Secret, Mike Solomon, Dennis Kovar, and many others, as well as from MIT, from the School of Science, and Mark Kastner, and from the Laboratory of Nuclear Science. Many, many people work together. In addition, physicists from Germany, under the leadership of Professor Scher, Professor Lucas Meyer, from Italy, Professor Roberto Battistone, who did an enormous amount of work for AMS. From Switzerland, Maurice Bourquin. From Spain, my good friend Manuel Aguilar. And from Taiwan, S.C. Lee, and also from many universities in China, in Russia, in many, many countries. The observation of rise of positron fraction has existed for 20 years. What AMS has done, what I reported today, is looking at this rise with a fine microscope, with a very good resolution and high statistics. As I said today in my talk, I've been doing physics in accelerator for many, many years. And seldom anyone in accelerator to do a 1% experiment. To do an experiment in space with an accuracy of 1%, it's really quite difficult. It's really made possible because of the existence of space station, and because of the support of NASA, from CERN, and from the participating countries. So this is a very happy day for all of us. As I mentioned before in my talk, we now discover many features of the rise of the spectrum. In a short time, the higher energy points, how they behave, how they drop off, how quickly they drop off, will be revealed. Many people ask me in my lecture today why I don't announce it now. And the answer is very simple. I cannot control statistics. It really depends on how long it took us to get enough events to make a definitive statement. We, of course, at the same time, measure many other things, such as electron spectrum, positron spectrum, proton spectrum, helium spectrum, nuclei spectrum. So there will be enormous amount of data that's coming out very soon. But I do want to take this opportunity to thank NASA again, and particularly Mr. Gerstenmaier and Trent Martin, Mark Sestelli, and Kim Bowie for make this possible. So I'm happy to answer any questions.
Great. Thank you very much, Dr. Ting. So before we begin the Q&A, just a quick reminder that you can find out more information about AMS and the International Space Station at www.nasa.gov/station. You can find the ways to connect with us on social media and follow the conversation there at nasa.gov/connect. So we'll now move on to the question and answer session. A quick reminder for those in the audience, just please wait until we get a microphone to you. Please identify yourself and your media affiliation. For those joining by phone, you can signal the operator that you have a question by pushing the *1 keys on your telephone. And I understand we have our first question by phone from Seth Bornstein of the Associated Press. Go ahead, Seth.
Yes, thank you so much. This is for Dr. Ting, or maybe if he can't, if there's an issue, Mr. Solomon. I guess trying to compare the differences between these results and Pamela, and the results between this and Pamela and Fermi, is it fair? I mean, these aren't the first results, obviously, that show what would be the footprints of dark matter, or a more prosaic answer. Are these? I know they're more precise. Do they add more heft? I mean, why are these more important than the other ones? Are they more substantial, more significant? I guess that's what I'm trying to get. Why is this better data than? Does this bolster the case for dark matter? You know.
Shall I answer this question? Can you hear me?
Yes, I can.
Yes. I can only comment on AMS experiment. It has an accuracy for most of the data of 1%. And it has a statistics unmatched by any other experiments. It is this fine feature set the difference between us and the rest of the experiment. As I just mentioned, it's just like you look at phenomena with your eye or with the electron microscope, you see different things. We see the spectrum increase, but the slope of increase becomes slower and slower and slower when you move to higher energy. We also see the positron to electron ratio is anisotropic. It's isotropic, meaning there's no fixed direction it comes from. These are some unique features. In addition, because we're so fine data, we do not see any sharp peaks. And we see the slope increases and seems to gradually flatten out. With more data, we will soon know when it drops off, how quickly it drops off. And then we will know what we see is from dark matter collisions or from pulsars. And this we should know with or precision and with or large acceptance.
Okay. Anything to add here in Washington?
I would just echo what Sam said. He said it very well. What we're seeing with Pamela and other instruments is a coarse measure of the spectrum, a very clear increase in the positron fraction, but the detail of the spectrum is what really provides us with valuable information, and that's coming from the AMS instrument. We're learning more about the spectrum with AMS.
Let's go ahead and take one more from the phone bridge, and then we'll come here to the audience at NASA headquarters. Next up, Alan Boyle, MSNBC. Alan?
Oh, thank you. This is probably for Dr. Ting as well. You mentioned the drop-off that would be expected in the fraction of positrons, and I don't think that drop-off has been seen in the observations so far. Does that give you pause, or do you feel as if it's just too early that the drop-off could be seen with more data?
When I give the seminar today, many people ask me, what is the behavior of the next point and the point beyond? And I said, took us many years to build this detector. We want to publish your data when there are enough statistics. And so when there's a drop-off, there's no doubt it has dropped off. And also we want to know how quickly it dropped off, how sharp it dropped off. And it is the way it dropped off that tells you whether it's dark matter collision or from pulsars. And this we should know soon.
Good. Anything to add here in Washington? Okay, let's go here in the audience. Our question.
Hi, I'm Miriam Kramer. I'm with Space.com. And I'm just wondering, so I know that the AMS was actually canceled, I think, in 2005 before it ended up going on up on the last Endeavour shuttle launch. And I'm just curious, and this is for anybody who'd like to answer it, sort of what does that mean either to you personally or sort of to the agency as a whole?
You guys want to say that? I can just say that, I don't know, I guess it teaches us patience is an important quality to have. There were times when we were uncertain about exactly what the future was going to be. We knew the quality of science was pretty strong and was pretty important, and the team hung in there, as I described earlier, and kept kind of pursuing their passion, their dreams, in pretty uncertain and turbulent circumstances. But they kept moving forward, all the teams, and eventually things worked out, and we got the instrument on orbit, and you get to see the results today. So I think there's probably a message to all of us when it looks kind of dark and doesn't look like there's a clear path forward. Fix your eyes on that point out in the future and continue moving forward and keep following your passion, and maybe things will break the right way and you'll get to see the results in the end. And then maybe they're just a tad sweeter that way than they would have been if it would have been a less turbulent path to the results.
And I'd like to add that, DOE has been supporting this experiment since inception, I guess in the mid-1990s. And our interaction with NASA has been fantastic. There have been little glitches, but the end product is here for all of us to see, and it's a happy day.
Good. Dr. Ting, sounds like Dr. Ting wanted to add something?
Yeah. I just want to mention we were moved off the manifest in October 2005. I made a mistake coming to NASA headquarters, meet the administrator, and I guess I didn't do my presentation too well. I was told your project is canceled. But even though it was canceled, DOE continued support us. In addition, most importantly, the Spanish, the Germans, the Italians, the Swiss, everybody believe the experiment is so important, we are going to carry it on, like Mr. Gerstenmaier said. I also want to mention, even when we were canceled, we continued to receive support from Mr. Gerstenmaier and from Johnson Space Center, what made it possible today.
Great, thank you very much. Let's go back to the phone line now with Jeff Broomfield from NPR. Go ahead, Jeff.
Hi there, guys. So my question is mainly for Dr. Ting. Does he believe that he's seen the first signs of dark matter today? And does he believe that AMS will eventually be able to definitively show whether this was dark matter?
Yes, I can answer you. What we have shown today only represents less than 10% of the data. And so with longer data collection time, eventually we will go to energy of trillion electron volt scale. I think with the AMS, there's no question we are going to solve this problem. We're going to solve this issue.
Okay, let's go back to the phone line again with Caroline Johnston of the Boston Globe. Caroline.
Thanks for taking my question. I was wondering if Dr. Ting could answer, how much more data do you think you need? How many more years or months of events to detect definitively whether it's dark matter or something else?
Caroline, nice to hear your voice. We do not know because it really doesn't depend on us. It depends on nature. If there's a sudden quick drop-off of the spectrum, this means we have found the origin of dark matter, in which case we will like very few events because the spectrum will drop off very quickly. If the excess come from pulsars, then it's going to drop off very slowly. Then we're going to collect quite a few more events at very high energies. I think the next year or two, we will know much better. We have some information now, of course, but with not enough statistics, it's probably better we do this carefully and systematically, make sure what we announce is really correct and it's not due to statistical fluctuations.
Okay, our next question comes from Mark Matthews of the Orlando Sentinel. Go ahead, Mark.
Thanks, guys. I appreciate the question. This next question is for anyone on the panel. I was looking for someone to help explain the relationship here between the findings announced today and the presence of antimatter in the universe. Thanks.
Well, I can answer this question.
I can answer that, or Professor Ting can. Let me throw my hat in first. I don't know of any connection.
Okay, Dr. Ting?
I think what DOE's opinion must be correct. So I agree with it.
Okay. Our next question comes from Monica Young at Sky and Telescope magazine. Go ahead, Monica.
Hi, thanks for taking my question. I'm wondering if you can make claims at this point on what mass range of dark matter particles we would have, and if those would be in the slider.
I couldn't hear the question.
I'm sorry. Would you mind repeating the question, Monica?
Certainly, yeah. I'm at mass range of dark matter particles that the AMS are there any constraints?
One more. You're cutting out just a bit, so try it one more time.
Oh, sorry about that. I'm wondering about mass range of dark matter particles. If the observations are able to.
Okay, so the mass range of the particles is the gist of the question.
If it's confirmed.
If it's confirmed.
We should be able to look to the mass range close to 1 trillion electron volt.
Okay. Let's move on.
Did you hear me?
Yes, we copy your answer. Next is John Heilprin from the Associated Press. Go ahead, John.
I'm wondering if the drop-off is more indicative of dark matter or pulsars. Can you say at this point?
We, this moment, have not decided how to phrase this because we don't have enough events. With time, we should be able to tell you whether it's drop off very quickly, in which case will be dark matter collision, means we have found dark matter, or it drop off very slowly, which means the positrons will come from pulsars.
Okay, anything to add here in Washington? Okay, let's go for one follow-up by Seth Bornstein at the Associated Press. Go ahead, Seth.
Thank you. Dr. Ting, I'm sorry to keep pushing. But in terms of at the moment, do you feel what you know now more bolsters the case that this is dark matter, or does it more bolster the case that it is pulsars? I mean, right now, which does this help more, or which are you leaning toward more at this moment?
For experimental physicists, it is extremely important not to have preconceived ideas. And you analyze the data and see what you get. And so better I do not have any preference. Because if you have a preference, you analyze your data according to your preference. And sooner or later, you may make a mistake.
Okay, before we begin to wrap and take the last few questions by phone, let me just do a quick check in the audience and just see if we have any additional questions here. Seeing none, let's go to Matthew Francis at Ars Technica by phone. Go ahead, Matthew.
Hi, and thank you. My question has to do with the results from the data are showing a remarkable amount of isotropy, meaning that the flux of positrons is coming from all directions. Now, correct me if I'm wrong, but it seems to me that if these are truly from dark matter annihilations, shouldn't there be strong anisotropy, particularly from, say, central galactic region? Could you comment on that, please?
Most of the people believe dark matter is distributed uniformly throughout the cosmos, and therefore their collision will produce isotropic positron distributions. Pulsars, on the other hand, has a fixed direction, and so it tends to give you positrons in a given direction, and therefore will be anisotropic.
Okay, our next question comes from Todd Halverson of Florida Today. Go ahead, Todd.
Thanks very much. Can you hear me?
Yes, I can hear you.
Thanks. I'm wondering, just trying to boil this down, are you reporting today that you think you've seen the first evidence of dark matter and that you're confident that the AMS will enable you to sort the issue out or definitively detect dark matter in the future?
I said our evidence support the existence of dark matter, but cannot rule out the origin come from pulsars. But I'm confident with enough time, because we will be on the space station for the lifetime of the space station, we should be able to solve this problem. Hopefully quickly.
Okay, let's go to back to NPR and Jeff Broomfield for a follow-up, and we'll make that next to last question. Go ahead, Jeff.
Sure. As I'm sure Dr. Ting and maybe some others are aware, not a lot of people, but there are critics of AMS. They say that the $2 billion price tag isn't really worth, the result we're seeing today, which is non-definitive detection of dark matter. I'd just like to give you guys an opportunity to respond to that criticism.
Well, this is the beginning of our publication. Physical review letters today inform me they will put all data on the front cover and also announce us to be, what is the term? Editor's choice and viewpoints. So every different person is entitled to their opinion. But the important thing is, AMS is there now. We are collecting data. We will be collecting data for the lifetime of the space station. With its unprecedented accuracy and with its sensitivity, we will explore a region which nobody has been there before.
Anything to add?
Yeah, I'd like to add that the cost of the space station is borne not only by the United States, but many international collaborators. 15 other nations contribute to the cost of the AMS. Excuse me. The U.S. contribution for AMS is comparable to the costs that we bear for other dark matter experiments. So our program at DOE is balanced between these three different ways of searching for dark matter with comparable expenses in all categories, including AMS.
Great. Let's take one last question by phone from Ken Kramer of Universe Today. Go ahead, Ken.
Hi, thanks for taking my question. For Professor Ting, there are different detectors on the AMS. I wonder if any of the detectors were more helpful than others in gathering the data, or were they all equally helpful? Thanks.
This is a very good question. We have many detectors. We have designed these detectors to be complementary to each other, and so that every signal we see is verified by a different detector. In this way, we're sure of our data.
Okay, so we will take one last question here in the audience for Miriam. Go ahead.
Hi, thanks. Miriam with Space.com again. I'm just wondering how the AMS data compares to what it was predicted to find when it was designed, and is the instrument sort of fulfilling the goals that were hoped for?
I couldn't hear the question. I'm sorry.
Could you repeat it?
Hi. I'm just wondering how the AMS data compares to what was predicted, or if this was sort of out of the blue, and is the instrument sort of fulfilling the goals that you had hoped for when it was designed initially?
I would say when we first designed the detector, we have hoped to have a sensitivity of 1% accuracy and to have a very good resolution. And we are very happy we managed to achieve this goal. As I mentioned at the beginning, the goal we set for AMS is normally not reached in accelerators, detectors on the ground. To do this in space really is a very challenging thing. So we are very happy we have reached this.
Great. Any final thoughts from here in Washington? Good. Okay, well, that's going to end today's media conference then. You can find out more information about AMS and the International Space Station at www.nasa.gov/station. You can find all the ways to connect with us on social media at www.nasa.gov/connect. I'd like to thank all of our speakers for joining us today and for their time, and thank you all for joining us today, and have a good one.